I hear a lot of noise, so if you've got your microphone on, please mute yourself. Again, as always, this is going to be a fairly interactive class, so do make sure to, I will be following chat on the side, but do feel free to ask questions and so on. I will respond. All right, so let's begin. We're going to sort of begin a new topic in today's lecture. And this sort of continues from the last topic that we covered, which was autoencoders. So, so far, we've seen that neural networks are universal approximators. They can model Boolean functions. They can model classifiers. They can perform regressions. We saw in the last class that they can extract features. So they can be feature extractors, classifiers, or predictors. But then here we have a new problem. In all of the previous cases, we considered neural networks that are functions that operate on or process a given input data. So they can learn to perform these tasks from data. But can networks generate data rather than operating on data? And can they learn to do so from examples? This is going to be the topic for the next 4 lectures, at least, actually the next 6 lectures. So here's the problem. You're given a large collection of images or faces. And based on all of these images and faces, we would like the network to be able to see all of these data. Let me see if I can draw. I should technically be able to draw with this. My pen is not working. So a network should be able to see these pictures and should be able to learn to generate a new figure such as this one. And so the question is, how can we actually train a network to do something of this kind? Or, for example, see a bunch of pictures of this kind and learn to imagine a new picture of this kind based on what it has learned of landscapes. So basically, in these problems, you're learning a distribution of a particular kind. In this case, the network would be learning the distribution of face images, and then we could draw a new face image from this distribution. Or here, from all of the examples to the left, it would be learning the distribution of landscape images, and we should be able to generate new landscape images by drawing from this distribution. But then when we're doing this, how do we even characterize a distribution, and how do we use a neural network for this task? So to sort of recap, we've seen how neural networks can perform classification or regression. We want to use neural networks as generative models that can model the distribution of our data so that we can draw samples from it. But first, we want to see what it means to have generative models. What is a generative model? And we're also going to have to figure out how to estimate generative models. In this context, we'll briefly touch upon expectation maximization. So what is a generative model? A generative model is the model for the probability distribution of some data, which I'm representing by the symbol X. So for example, a multinomial distribution or a Gaussian distribution. All of these are models for probability distributions of different kinds of data. In a computational sense, the computational equivalent of a generative model is a model that can be used to generate data with a distribution that's similar to some given data X. So in a typical setting, you can think of your generative model as a box which takes in some random seeds, and based on these random seeds, it outputs random samples which look similar to the kind of data that you're trying to model. And in this context, something that we won't touch on right now is where do these random seeds that we are speaking of come from, even that this box will use to generate data. So here's the general principle over here. You're given some set of observed data, and you want to model the distribution of this data. So to model it, you're going to choose some model, P of x semicolon theta, where theta are the parameters of the model. And then we want to estimate the theta such that P of x semicolon theta best fits the observations that you have that you have begun with to learn this distribution. And in this process, you want to learn this P of x semicolon theta. So this theta are the parameters. This is a parametric function. And you want to learn this distribution that it not only fits the data that you have, but also generalizes to data outside the training set. So let's look at some examples, some trivial examples, like the category distribution. If you have a dice, then the dice can have 6 outcomes, 1 through 6. And when you roll it, each outcome is going to have some probability. So if you keep rolling it, if the dice is not fair, the different outcomes will occur with different frequencies. And so now our parametric distribution for this dice is a category distribution which assigns probabilities to each of the 6 possible outcomes. Now, how do we sort of determine what this distribution is? You might start off by just observing a lot of outcomes. So for example, your dice shooter might roll a whole bunch of numbers. And let's say you plotted all of these numbers. You plotted the histogram of all of these numbers, and you found the histogram to look like this figure over here. Now, if I were to give you the choice between this distribution and this distribution, and if I were to ask you which of these two distributions do you think better represents the probability distribution of the dice, which one would you choose? The green one, right? So similarly, let's say we look at something like this. This histogram to the left is actually the actual histogram of log energy values from a speech signal. And when I plot the histogram, it had that shape. Now, if I decide to, if it kind of looks Gaussian, so if I decide to model this distribution as a Gaussian, then given the choice of the yellow, the green, and the red Gaussians, which of the 3 do you think is most likely to be the distribution of this data, the genuine distribution of this data? Anyone? The red one, right? So why did you choose the red one? Can you tell me? Best fit in what sense? It most closely matches the histogram, right? When you say it most closely matches the histogram, you made an assumption. And what was that assumption? Can anybody articulate that assumption? Maximum data falls under the curve, same mean and variance. Over here, in this case, there are no mean and variance, right? So the underlying assumption that you made was that this data that you observed are actually very typical of the true distribution. And so also over here, you assume that this histogram would be very typical of the distribution that it was drawn from. And so you chose the distribution that best matched this data. And when I speak of this, there's a notion of a match, but underlying was the assumption that we spoke of earlier. You assume that the world is a boring place, that the data you observed is very typical of the process. And so the consequent assumption was that the distribution for that data has a very high probability of actually generating the data that you observed. Now, this is not necessarily true, but this is an assumption you made. And so what you did over here was that of all the choices that you were given, you sort of chose the distribution that was most likely to have generated this data. You may not have realized this, but then you chose a distribution which assigned high probabilities to outcomes that were most frequent and low probabilities to the outcomes that were most infrequent. So you selected the distribution that has the highest probability of generating the data without even thinking about it explicitly in this manner. So let's actually try to formulate it. Let's see how this thing works. Now here, for example, if I gave you this histogram of outcomes from a dice, and if I were to ask you, what do you think the probability of 1 is for this dice? What is the answer you would give me? Anyone? If I asked you, it's 1/6, really? It's going to be n1 divided by the sum of all of the number of outcomes, right? n1 over the sum of all. And so where does that come from? If I consider all of these outcomes and consider the total probability of this particular data, then we know that the outcome 1 occurred n1 times, 2 occurred n2 times, 3 occurred n3 times, and so on. So the total probability of the data that generated this particular set of outcomes is going to be proportional to the product over all possible outcomes of the probability of the outcome raised to the number of times that outcome was observed. This pi raised to ni is the probability that the ith outcome was seen ni times, because the ith outcome has a probability pi and it was seen ni times, and this is over all possible outcomes. Now, we're going to take a log first, simply because a log converts multiplications to additions. So this log of this probability is the logarithm of the probability of the set of outcomes that generated this histogram. And you would be choosing the probabilities for the 6 outcomes that maximizes this log probability. So also in the case of the Gaussian, what you would be doing here is you would be choosing if you have a bunch of independent observations, the total probability of all of the observations is the product over all of x of the probability of the individual observations. We take the log of it, and you'd be choosing the parameters of this distribution that maximize this log probability. So that's going to be for the Gaussian, the parameters are the mean and the variance, and you'd be choosing the mean and the variance that maximize the log of the product over all observations of the Gaussian computed at that observation, where the Gaussian has mean mu and variance sigma squared. And of course, if I actually consider the log, the summation product inside the log becomes a summation outside the log. P raised to ni, the log of p raised to ni is ni log pi, and so on. So just sort of simplifying it, the log probability would just become the sum over all outcomes of ni times log pi in the first case. And in the second case, it's going to be the sum over all outcomes of the log of the Gaussian computed at that outcome. And if you just went through the math and you actually maximized this term, you would find that the probability compute assigned to the ith outcome pi is going to be ni raised to n, where n is the total number of observations. So the formula that you just gave me, which is the proportion of the outcomes and the number of times any particular outcome was observed to the total number of observations, that is actually just a maximum likelihood estimation. So also, if you maximized this term with respect to mu and sigma squared, you would find that the mean of the Gaussian is simply going to be the mean of the data, and the variance of the Gaussian sigma squared is simply going to be the variance of your data. So these are formulae that you've encountered in school. And as it turns out, these are actually formulae derived based on the maximum likelihood principle. The formulae that you would get if you assumed that the data you observed were extremely plausible for the particular distribution, and you chose the specific distribution that assigned the highest probability to this data. And so we will have our first poll. Yeah. I'm assuming everybody sees the poll.
Prof, shall I release the polls on Piazza as well for the people in classroom?
Sure.
Okay.
No error with any one. This is just, again, the polls are intended only to drive a point home, right? And zoom poles are very convenient. Okay, so I'm going to stop this over here. And what are the answers for the first one?
True.
Second, also true, right? And yeah, most of you actually got that right. Anyways, and some of you hurried just to get on the poll, and you got it wrong, but I'm sure everybody knows the answer. So we get an idea of what maximum likelihood estimation actually does, right? But then here is a situation. Sometimes the data that are provided to you may be incomplete. They may be insufficient to write out the complete log probability. In that case, you can't just use this business of differentiating and equating to zero or anything that's analogous to that process to estimate your model parameters directly. And why could the data be incomplete? There can be multiple reasons. It can be because the data themselves have missing components, or because of the structure of the model that we are using to model the distribution of the data, like mixture models, where the model has multiple generative stages. The actual data you observe may not be sufficient to characterize every aspect of this distribution. So let's take a look at each of these two examples. First, consider this one, where the data themselves have missing components. So, for example, let's say I'm trying to compute a Gaussian distribution for these data. These are all vectors. Each bar represents a vector. Each little square in the bar represents one component of the vector. And any square that's blacked out is a component that is not known to you. This kind of data occurs very frequently. For example, people who take census, the census board takes census of people, and it asks them various questions, including, what is your income and whatnot. And amongst these, some people will not answer some questions. For example, so a person might choose not to answer about their race, or a person might choose not to answer about their income or whatever else. And so many of these vectors are going to have missing components. In this case, if you want to compute the Gaussian distribution of the data, a Gaussian distribution for the data, would you be able to do it directly? Anyone? What would the issue be? I'm getting no answers. Can you hear me? Hello? Imputation. The issue is, yeah, I'd like to see some more answers. Guys, respond. This is on Zoom. All right. So here's the thing. When I have incomplete components, right? Some terms are missing. I'm not going to be able to compute the mean over all the data because this guy is missing. It's even worse when I'm trying to compute covariances, because if I have something of this kind, then many pairs are going to be missing. You're simply you don't have enough data to simply compute the Gaussian directly, right? But then let's look at it from the maximum likelihood perspective. You're looking at it from the formula perspective. You want to estimate the Gaussian given this collection X of complete data. And so when you are doing the maximum likelihood estimation, you're actually taking the log of the probability of the data, where this distribution is actually defined over the entire vector, not over any subset of components. Unfortunately, if you want to compute this guy over here, that means you need to be able to compute log of P of X, but then X is not complete. Some components are missing. And so you have a problem, right? But then if you actually look at what you have observed, these green components are all the data that you have observed. And these are incomplete vectors, some missing components. And some of the components are missing. All of these blacked components are missing. And so the complete data that you would want to see, if you actually wanted to be able to compute the probability distribution using your Gaussian, which is defined on the complete vector, is going to be the union of the observed components and the missing components, except the missing components are not present. But then, if I look at the maximum likelihood principle, the maximum likelihood principle does not maximize the likelihood of the missing components. You're only allowed to maximize the likelihood of whatever it is you have observed. So your assumption here is that whatever you have observed is very typical of the process. And so you would actually want to estimate your means, your distribution parameters to maximize the likelihood of whatever it is that you have observed. Unfortunately, the probability distribution that you have here is a Gaussian that is not defined merely on what you have observed, but on a combination of what you have observed and what has been hidden. And so the actual distribution that you get, P of x, which is your Gaussian, is defined on the combination of the observed and missing components. So if you want to get only the probability of the observed components, you're going to have to think of this total data, complete data, as a combination of the observed and missing components, and you're going to have to integrate out the missing components from the distribution. So this is the marginal over the observations. And so you would need to compute P of O, this guy, by integrating out the missing components, and then you can compute the log probability over the observed data. And then you can perform your maximum likelihood estimation by estimating your mean and variance to maximize the likelihood of the observed data. Did this make sense? So, Anthony, what was your question? Can you repeat that? I'm not sure I understood.
Oh yeah, I was just wondering what the summation sign over O, like O element.
So O are all of the
that
observed
disturbance.
vectors. So this is the data. These are the set of incomplete data vectors that you observed, right? Remember, earlier when we had complete data, we actually were doing this, were we not? We were summing over all vectors, and you were summing the log probability of the vectors, correct?
Yes.
Okay. But now you don't have complete vectors. Each vector is now incomplete. And you're just going to be assuming that each of these incomplete vectors is independently drawn. So you're summing over your incomplete vectors, and you're maximizing the log probability of the incomplete vectors. But because this is all you have observed, right?
Yes.
Okay. And so to answer your question, I'm saying that complete data X is going to be the union of the observed and missing components. Anytime you have P of xy, you can get P of x by integrating out y, right? So we are integrating out the missing components to get P of O. Did that answer your question, Arpit?
Yes, I understand.
Oh, okay.
Thank you.
Yeah, I think
Right?
I understand.
And so the problem really here is that you can't solve this. You're trying to maximize the log of an integral. There's no closed form. And that's a challenge, right? You can't do this. So you see how having missing components makes this problem challenging. Anybody? Any doubts? I'm assuming not, right? So the other issue that you can have is when there's incompleteness because of the structure of the model, like in mixture models. So for instance, let's say you have some data whose distribution has this very ugly shape over here. Now, it's not easy to characterize this shape. I don't even know what kind of probability distribution function would give this shape nicely and cleanly. So what we often do in this kind of situation is to model it as a mixture of many distributions. You try to fit it by using, but in this case, a typical one is a Gaussian mixture. You say that this upper ugly shape can be obtained as a weighted sum of many Gaussians, where the weights sum to 1. And now the probability the problem over here is that you want to, you're given a bunch of data from the actual distribution, but you're modeling the probability distribution over here as a mixture of Gaussians. And so to compute or estimate the distribution for the data, you need the parameters, the means and variances, and this mixing weights for all of the Gaussians. And once you know all of those properly, you have a formula for the distribution, a reasonable formula for the distribution of the data. This is a standard Gaussian mixture model. Now, the problem here is that there's an underlying generative story. So did the idea of a Gaussian mixture model make sense to all of you guys? If it did, just raise your hand so I know, or give me a thumbs up. I'll wait till about 50 hands are raised because we have 130 people in class. I need to know that more than 6 people are paying attention. I'll wait. If this made sense, guys, raise your hands. I'll wait. That's awfully slow. I'll keep waiting. Thank you. That's 50. The next time, please do respond because I will wait for you, right? So the problem with trying to estimate Gaussian mixtures is that a Gaussian mixture distribution actually has an underlying generative story, like every other generative model. It says that the actual data are obtained by drawing from one of each of these Gaussians, and exactly which Gaussian any data instance is drawn from is chosen according to P of K. So there's a two-step generating process. In the first step, according to P of K, you would choose one of the Gaussians. In the second step, you would draw an observation from that Gaussian. And so if you want to learn the distribution of the entire data, you really want to, you need to know the details of the entire process. Ideally, in this kind of situation, if you know the details of the entire process that generated the particular observation, you would know which Gaussian every observation came from. For instance, if your data was generated by a mixture of these 3 Gaussians, the green, red, and blue, then for every observation that you had, you would know which Gaussian it came from, whether it came from the blue or the red or the green. If you had this information, then estimating all the parameters of the distribution is very easy. All you would do is segregate out all the vectors that came from the blue Gaussian into a blue bundle. You'd segregate out all the vectors that came out from the red Gaussian into a red collection, and all the vectors that came out from the green Gaussian into a green collection. And then, now we know that all of these came from a single Gaussian. You can just use all of these to estimate the mean and variance of the blue Gaussian. You know that all of these came from the red Gaussian. You could use them to estimate the mean and variance of the red Gaussian. And so also, all this collection, which was segregated out based on the knowledge that these vectors were drawn from the green Gaussian, can now be used to estimate the mean and variance of the green Gaussian, and your problem is solved. But then the challenge here is that, so did this make sense to you guys over here? Again, give me raise your hands if it did. Please be prompt. Yes. Each column is a vector, right? Which is drawn from the Gaussian. So I had 40 people raise their hands out of 131. This is kind of bad. I'd like the other 80 people to also raise their hands. And so I know, right? Okay. So now the problem is, the point is, it doesn't matter, right? The fact that it's overlapping doesn't matter. The idea is that if I think of the entire model, the model says that the data are being drawn from a mixture of 3 Gaussians. There are some data points which could have come from any of these Gaussians if you didn't know which Gaussian it came from. But then if you knew which Gaussian it came from, then you can definitively say that when I drew this data point, I first selected the red Gaussian or the green Gaussian. That's part of the drawing process, right? And again, you want to remember that this business of overlap also accounts for these portions of the curve, right? If the Gaussians never overlapped, then you would have some regions where the overall distribution was expected to be zero. That doesn't happen. So the overlap accounts for those regions of the overall distribution. But then the problem we have here is that we are not given the actual Gaussian for each observation. Our data are incomplete. For each observation, we also want to know the Gaussian it came from, but all we have are the observations alone. And so when I want to perform maximum likelihood estimation, as before, I can only maximize the log likelihood of what it is that I have actually observed. But then the probability of observing any, and in my case, what I have observed is the actual data itself. And the probability of any data vector sums over all Gaussians. And what it sums is the joint probability of the Gaussian and the observation, which is to say, it sums the probability of selecting the Gaussian and then choosing that observation from that Gaussian. This is summed over all Gaussians. And so if I want to perform maximum likelihood estimation, when I'm only maximizing log of P of O, I'm maximizing the log of the sum over all Gaussians of this term. And so once again, I end up with a summation inside the logarithm. And now this becomes challenging because now I can no longer optimize this directly, right? So did this make sense? How not knowing the Gaussian makes things challenging. All right, I'll just continue, okay? And so what we find is that the presence of missing variables, or rather the absence of knowledge of some variables, requires these variables to be marginalized out of the distribution by summation or integration. So in this case over here, for example, we were marginalizing out the k by summing over k. And this results in a maximum likelihood estimate of the form where you have the log of a summation or an integral. And this typically doesn't have closed form solutions. And we need effective, efficient, iterative algorithms for this purpose. And so the real challenge is this, that whenever you have missing information or missing observation, missing data, like in the case of the Gaussian, where we were trying to estimate the Gaussian from incomplete data vectors, you had some Gaussian components that were missing. In the case of the Gaussian mixture, you were missing information about which Gaussian any vector came from. And whenever you have a situation of that kind, the missing data have to be marginalized out, which means that they have to be summed or integrated out. And so you end up with a summation or an integral inside a logarithm. And now this results in a problem where direct optimization is not feasible. So given that direct optimization is not feasible, can we get an approximation to this optimization that's more tractable? Something without a summation or an integral within the log. And for that, we're going to introduce something called the variational lower bound. Now, again, observe that the log of P of O, where O is the observed data, is the log of the summation over all of the over H, where H are the components of the data that we didn't observe, or the components of the generation process that we didn't observe. So this is the log of the summation over H of the joint probability of H and O. This doesn't change if I multiply and divide by a Q of H, where Q of H is some other probability distribution over H, right? So is this making sense to you guys as a formula? I'll wait to see 50 hands raised. All right, thank you, right? And so here's where the trick comes in, right? Observe that we have the log of the summation of Q of H times something where Q of H itself sums to 1 because we said Q of H is a distribution over H, right? Now the log is an interesting function. It's a concave function. If I plot log of X versus X, it's going to look like this curve on top. Now take any two values X1 and X2. Any point between X1 and X2 is a convex combination of the two, which is going to be some Q times X1 plus 1 minus Q times X2, right? So this is going to be a weighted combination of X1 and X2. Now this here is log of X1, this here is log of X2. If I draw a line connecting the two, this point here, the value on the line at this Qx1 plus 1 minus Qx2, this is simply going to be the weighted average of log of X1 and log of X2. So this point here on the red line is going to be Q times log of X1 plus 1 minus Q times log of X2. On the other hand, this point on the log curve, not on the straight line, but on the log curve, this is the actual logarithm computed at this value of X. So it's log of Q times X1 plus 1 minus Q times X2. And because of the shape of this curve, the log of the weighted average of X1 and X2 is always going to be greater than or equal to the weighted average of log of X1 and X2. So did that make sense to you guys? Q times log X1 plus 1 minus Q times log X2, which is the point on this line, is always going to be below log of Q times X1 plus 1 minus Qx2. Does this make sense? If it didn't, let me know, because we're going to build off this. I'll wait. The 24 people, that's it. So, okay, where did I lose you? It appears this sort of went over people's heads. I'll wait. What was the doubt here?
Yeah, I don't know what.
I can't hear you. Can you come closer to the mic?
Yes, no, I'm not.
Guys, whoever is talking, can you please mute your mic? Okay, if you're not paying attention to class, please log off the Zoom. You are disturbing the rest of the class. And if you don't intend to pay attention enough to even raise your hand, then I request you to drop off the class, because you waste my time because I wait for half of the class to sign to indicate that you're listening to me, right? So here's my last call. Did you get this or not? I'll wait for 50 hands to be raised. Thank you, right? All right. And again, if you're not paying attention, if you don't intend to raise your hands, I request you to drop off. You're wasting my time, okay? So here's the thing. In general, the log of a weighted convex combination of x's is always going to be greater than or equal to the convex combination of a log of x's. This is what we're going to be depending on, right? And so going back here, the log of, again, when Q of H is a probability. So this is a convex combination of P of H comma O divided by Q of H, right? And so the log of the convex combination of these guys is always going to be greater than or equal to the convex combination of the log of these guys, log of P of H comma O divided by Q of H. So is this making sense based on what we just saw? We have not said anything about how Q of H is chosen yet, right? But did this make sense, Sharak? Assuming that, so this is going to hold for every single Q of H. It doesn't matter how you choose Q of H. This formula is generic. If Q of H is a distribution over H, this will always hold. this term to the right is always going to be a lower bound on the term to the left. And so we have this situation. We know that this guy here, this term here is simply log of the summation over h of p of h comma o, which in turn is simply log of p of o, right? So log of p of o is always going to be lower bounded by a convex combination of convex sum of log of p of h comma o divided by q of h, regardless of how you choose q of h. So this guy is what is called a variational lower bound, or an empirical lower bound, as you will see shortly, on log of p of o. This term to the right is never going to be greater than log of p of o. Right? Is this making sense? Okay. And so what does that mean? Let's say I have a parametric probability distribution. And so this probability distribution is going to be the log likelihood of my data, which is this term over here, is going to be a function of theta, right? And as I vary my theta, that's going to have a shape of this kind that I've shown over here. And the term to the right, this over here, is a lower bound on that, meaning at every value of theta, it's guaranteed not to exceed the red curve. So it's going to be a function of this kind. And so if I raise this guy, if I choose my theta to raise this guy, so meaning if I chose a theta over here, I can generally expect that the corresponding f of theta over there. So let's consider two thetas. This is one theta and this is the other theta. The lower bound at this theta is greater than the lower bound at this theta. So I have reason to expect that the actual f of theta over here, which is the log likelihood of my data, over here is also going to be higher than the log likelihood of my data over here. That's an assumption. I have reason to believe that. But specifically, if I have a tight lower bound, by a tight lower bound, I mean that my lower bound is very close to my log likelihood function. Then, if I choose my theta such that my tight lower bound is maximized, I can expect that at that theta, even my log likelihood f of theta will be maximized. Does that make sense? It's not a guarantee. It's a belief, right? So did that make sense? Thank you, right? And so here's what we are going to do. The tighter this lower bound is, the more likely you are that if you maximize the lower bound, the original function is also maximized. So we're going to try to make this lower bound as tight as possible. And so what we will do is to have a two-step process. In the first step, we're going to choose our Q of H such that this term to the right is maximized. We know that the term to the right is never going to exceed log P of O, regardless of what you choose Q of H as. But I'm specifically going to choose Q of H such that this term to the right is maximized. Once I choose that Q of H, then now I no longer have a summation inside the log, right? I'm going to fix that Q of H and maximize, choose theta to maximize this term. And then, so basically what we're going to do is iteratively choose a Q of H at any point such that the Q of H becomes a tight function. Tight lower bound. The Q of H gives me a tight lower bound. And then at that tight lower bound, I'm going to maximize the lower bound. And then based on that, I will actually go back and maximize Q of H. And if you want to see the details of how that works, I suggest you go back and look at the slides. I won't spend a lot of time going over the details of it. But the basic idea is that for this, the critical component is finding a Q of H that tightens the lower bound. If the lower bound is not tight, if it's loose, then just maximizing this term to the right doesn't tell you anything about what's happening to the term on the left-hand side. You want the right-hand side to be a tight lower bound. And so the first thing we will do is to try to find the Q of H that maximizes this guy. And Q of H we saw is just a probability distribution, meaning Q of H is always non-negative and it sums to 1. And you could maximize, and you could choose Q of H, compute Q of H in any manner. Q of H could also be just a neural network over H's, or it can be some other function. And maximizing this term, Q of H, finding Q of H such that this term is maximized may not be trivial. If you choose a neural network to model Q of H, you will need gradient descent with backpropagation. But then for other kinds of models, you may actually have a closed form for Q of H for maximizing it. Now, the point is this: when I'm maximizing this term over here, that already depends on theta, right? Because the term inside the log includes theta. And so the optimized Q of H depends on theta, which is why we need this iterative function. The optimal Q of H is going to depend on theta. Once I choose a Q of H, I can go back and optimize theta. But then for the new theta, the optimal Q of H is likely to be different. And so I'm going to have to use that to go back and optimize Q of H and keep iterating the process. As it turns out, there is a specific Q of H that actually does give you the tightest possible lower bound, where if I say Q of H is the conditional probability of H given O. If I say the conditional Q of H equals P of H given O, then plugging in that Q of H will show you that this lower bound is actually the log probability of O itself, which is the largest possible value that it can take. So if you say Q of H is exactly equal to P of H given O, then your lower bound becomes the function itself, right? But more generally, computing this guy is not going to be easy, and so you're going to use approximations. And so overall, the first step in the iteration is going to be to find the Q of H that maximizes this term to the right. That's called the empirical lower bound. You're going to maximize the empirical lower bound. And then or choose the Q of H to maximize the empirical lower bound. And then you'd fix the Q of H and then choose the theta to maximize this term to the right, which also does the same thing, right? And so if I want to choose this term to the right, that's simply, if I want to maximize this term to the right for a given Q of H, that's simply going to be the sum over all H's of Q of H log P of H comma O minus log Q of H, because the log of P over Q is going to be log of P minus log of Q. And the second term, Q of H over here itself, once it's fixed, is no longer a function of theta. And so you can just say that, you're going to choose the theta to just maximize this first term, which is what you'd get over here. You're going to choose the theta such that for the given Q of H, the convex sum of log of P of H comma O over all H's is maximized. So this is the basic theory of it. There's a two-step process. I'm going to find the Q of H's that maximizes this lower bound. Then I'm going to fix the Q of H. And then using that Q of H, I'm going to maximize this term to the right with respect to theta. And I'm going to keep iterating between the two. And so this is what we will call training by maximizing a variational lower bound, or also called the empirical lower bound, the elbow function. And this is what most papers on the subject are going to tell you, right? Now, did all of this, H is the hidden data idris. It's the stuff that you didn't see. Like when I was trying to estimate the Gaussian with incomplete vectors, H would be the components that I didn't get to see. Or when I was trying to learn a Gaussian mixture, then H would represent the Gaussian that each vector came from. Did that answer your question, Idris? Right, okay. And so the special case, expectation maximization, is where for Q of H, I actually use the conditional probability of H given O. And here in the iterative process, if theta superscript k represents my current estimate of the parameters, I'm going to estimate Q of H as P of H given O using those parameters. Then I'm going to plug that in, and then I'm going to be maximizing the convex combination of the joint probability of H and O using this particular value of Q of H to get the next estimate for theta. So this is the EM algorithm, which is the special case where Q of H is the conditional probability of H given O. And the generic case, Q of H can be any other function, right? So here's the second poll. Let's release the second poll. To answer this, yes, as you keep increasing keep iterating at each point, the log likelihood of your data are expected to increase. When the log likelihood of your overall data computed using the specific estimate for theta you currently have stops increasing, then you're done, right? So let me stop this. This has been, I'll end this poll and let's share the results. What did we get? Most of you got the answers right. Let me say this. EM is an iterative algorithm that can be used to estimate probability distributions when the data are incomplete and have missing components or variables. It iteratively maximizes a lower bound function. It does not mean that there's any closed form formula. All you're doing is sort of simplifying the formula that you're optimizing, but there's still no guarantee that your formula will have any closed form. And this empirical lower bound itself is a lower bound on the actual log probability of the training data as computed by the model. And so it's going to be a function of model parameters. And it's a lower bound, so it can never be greater than the log probability of the training data, right? So everybody with me so far? Expectation maximization, because in the specific case of expectation maximization, you are taking, when you think of this guy, this is the expected value of H given O, basically. So you get an expectation that you maximize, but we'll get into that. It doesn't really matter to us, right? So what is this EM? So that's so much for math, right? But I don't know about you. Math is very opaque to me. It doesn't make a lot of sense. So let's try to see what happens in the real world, right? What does it practically do? What is the intuition behind it? And how does it resolve the problem of missing data? Let's look at two examples. There could be incomplete data because the data themselves have missing components, right? So for example, you have this issue. We wanted to compute a Gaussian using these incomplete data. Every data vector O has some missing components M. The complete data would include both the missing and the observed components, right? So suppose I gave you data of this kind and you were kind of naive. What is the first thing you would do so that you can to make this data amenable to estimating a Gaussian? Anyone? What would you do? Fill in the missing values, right? It can be so. Consider any single vector. What you would do is to try to fill in this guy. But how would you fill this in? Fill it in with appropriate values. And what would the appropriate values be? You could interpolate. You're basically going to use this. You're going to fill this in using a value that matches the rest of these guys, right? You assume that all of these values have some kind of correspondence. And so when I give you all of these other green values, this black value, this black missing component can't be anything at all. It has to sort of align up with the rest of the feature data that you saw. And specifically, if you considered all possible values that you could have over here that align up with the data that you did observe, that's probably not going to be unique. That's probably going to have an entire distribution all by itself. So what I will do is to make many copies of this vector and fill in this missing element with every plausible value of this missing component that kind of matches up with the rest of the vector. And any specific value, and each of these values is going to occur in proportion to the conditional probability of that particular value. So for example, over here, if I find that the value 7, given all the rest of the components, the value 7 is more probable than the value 3, then I'm going to make many copies of this, and I'm going to fill in 7 in some of these copies and 3 in some of these copies. And 7 is going to be filled in more frequently than 3. Basically, the question you ask yourself is, if I saw an infinity of copies of this vector, what proportion, or a very large number of copies of this vector, what proportion of those copies would have 7 here, and what proportion would have the value 3 here? And so you're going to fill in those values according to those proportions. That make sense to you guys? Right. And so what you would do is you're going to fill it in with every plausible value, but in proportion to their probability. And so now every one of these vectors is going to become a giant bundle where every plausible value for this component is filled in proportion to its posterior probability. And now you have a collection of completed data. And once you have completed data, you can compute your probability distribution, except where did this P of M given O come in from that you used to fill in the data? That's going to come from a previous estimate of the model. And so if you filled in everything that way, then now you have a large collection of completed data. And from these completed data, you know what these values are. You're going to have, each of them is going to be filled in proportion to their posteriors. You can plug in all of those into a formula, and it turns out that when you work your way through the math, using these completed data, we know exactly how to compute means and variances. And you're going to get a formula for the mean, and you're going to get a formula for the variance. I haven't actually worked it out over here. I've just sort of written it down to show how this worked out. But the integral over here is simply indicating that every possible value of the missing components has been filled in, right? So you're going to be summing over all of these, which means you end up with an integral. But that's just how the arithmetic worked out. And so here is the EM. This is the EM algorithm. In this case, if I were using EM, so the specific formulation I just gave you sort of assumes that you're filling these in with the exact posterior probability of those components. If you're filling these in with according to the exact posterior probability, you get an expectation maximization algorithm. If you fill these in according to an approximation to the posterior probability, then you're going to get a different variational method, which is very similar to EM, but both of them would work. And so in either case, what you would do is you would initialize your model parameters, and then for each data vector, you would complete the data vector in every possible way using a posterior probability distribution that's for the missing components, computed using the current model estimates, then use those to estimate the new model parameters. And then using the new model parameters, you're going to go back and complete these missing components yet again, and use the completed data yet again to re-estimate the model parameters. And you'd keep repeating this process until the entire thing converged. So Josh, this is not expensive. Why? Because you actually, in this case, you would end up with a closed form solution. But then to answer your question, if it is so expensive, if it were really expensive, what would your choices be? Any suggestions? Perfect, exactly, right? You don't need to fill it in every possible way. You can just sample the posterior and it should still work, right? So that was when you actually had data missing. But then let's try to look at a situation where you have missing information, like in the case of the Gaussian mixture, right? In the case of the Gaussian mixture, you don't know which Gaussian any particular vector came from. So our data are incomplete. What we want is the join, along with every vector, you also want to know which Gaussian the vector came from. But then that information is missing. And so here's what we can do. For each vector, so let's say this vector represents maybe some value over here, right? Then I can just ask myself, what if I consider this point? That's going to be, that was supposed to be a straight line. My apologies. You say, if I saw a large number of instances of this value, what fraction of them came from the red Gaussian? What fraction of them came from the blue? And what fraction of them came from the green? So that's going to be the posterior probability of the red, blue, and green Gaussians, right? And so every Gaussian was capable of generating this vector with different probabilities. So what will I do? I'm going to ask myself, if I saw a very large number of these vectors, how many of these would have come from each Gaussian? And then I'm going to fill in the Gaussian index for all of these copies, but they're going to occur in proportion to the posterior probability of the Gaussian. So for example, the fraction of these copies that I'm going to assign to the blue Gaussian is going to be proportional to the posterior probability of the blue Gaussian, given that X. The fraction that I assign to the green is going to be proportional to the green Gaussian, given that X, and so on, right? And now what happens is that every data vector now has been completed, except now I have many copies of it. And every copy has a definitive assignment to a Gaussian, right? And the assignment to the Gaussian was computed according to a posterior, which is P of K given O, which can be computed if you know about P of K and P of O given K. These are model parameters, and these are parameters that we got from a previous estimate of the model. And once we have that, every incomplete data vector has now been completed, right? Although I'm only showing 3 bars over here, you should assume that this bar with the blue dot represents as a large number of copies of the vector, where the number is in proportion to P of blue given this observation vector. So also this one represents a large number of copies, where the number is in proportion to P of green given the vector. And this is in the number of copies here is in proportion to the to P of red given the vector. And now that we have the completed data, I can just segregate them out. I can copy over all the blue vectors into a blue bundle, all the green vectors into a green bundle, all the red vectors into the red bundle. And from those, I can just compute the means and variances of the individual Gaussians. So we've simplified the problem and we've solved it, right? So how many Gaussians we do to use? That's part of the Gaussian mixture model. It's kind of slightly tangential to our discussion for the next couple of classes. The only reason we're even going over it is because we're sort of trying to introduce the concept of completing data, right? But did this whole process make sense? What we were doing so far, right? And I'd like to see a few more hands raised, because we're going to be using this. Thank you, right? And so here's what you would do if you were trying to train a Gaussian mixture model for the data. You'd initialize your model parameters. Then you'd go over all of your data instances. And for each of the data instances, given the current model parameters, you'd compute the posterior probabilities for all the Gaussians and then complete the data. And then you'd use the completed data to re-estimate your model parameters, and the whole thing would just work. So the general concept here is this: you complete the data, regardless of whether it's, missing data components or missing information about the generating process. You complete the data by considering every possible value of the missing variables and fill in the missing values in proportion to their posterior probability. This is going to give you a collection of completed data, and then you can re-estimate the parameters from the completed data. So this is the basic idea behind the entire approach of both expectation maximization and the business of maximizing your elbow, the variational lower bound. The key challenge over here is how do you compute the posterior probability that actually that you use to fill in these data, right? And there's another challenge, what this business of completing the data. In some cases, if I complete the data by considering every possible value for the missing data variables, I wouldn't need to explicitly do it. I can work out some math that gives me simplified formulae with some expectations. In other cases, as Josh pointed out, that's not going to be feasible. So what I can do instead is to simply complete the data by sampling the missing values from the posterior probability that I have computed. And then after having completed it by sampling the missing values, now I'm going to have completed data, and I can just go ahead and use the completed data to estimate my model. So estimate my model parameters. But then once I've estimated my model parameters, I have new parameters. I can use those to re-estimate my posterior probabilities and use those to complete the data yet again, and keep doing this until the likelihood assigned to my data by the model saturates. So did this entire process make sense to you guys? All right. So just moving on. Here's the overall EM principle, but the general principle of estimating model parameters by maximizing a lower bound. Remember this. Initially, some data or information are missing. We're going to initialize the model parameters. Then we're going to iterate this. We're going to complete the data according to the posterior probabilities computed using the current model parameters, either by implicitly considering every possible value or by explicit completion through sampling using the posterior probability distribution. And then using the completed data, you're going to re-estimate the model and you're going to iterate. This is the whole process. And once you state it in this manner, the process actually becomes very intuitive and simple, right? Any questions? This makes sense. Okay. All right. And so here's your poll. All right. We have only 116 responses so far. But okay, I'll give you the answer. To answer your question, Raj, the convergence criterion over here is that you expect the log likelihood of your data to keep increasing as you go through the iterations. If the log likelihood increases, you think the model is better. All right, so let me continue. Most of you got the answers right. Let's take a look. In each iteration, we complete the data by filling in the missing variables. So sorry, I muted myself when I was wondering. Okay, to answer your question, Ritu, in many cases, so we only use every possible value. I got muted by mistake. So when we miss, we only use every possible value when we are able to use a closed form, derive a closed form formula that implicitly considers them all. More generally, we won't be able to use every possible value, in which case we'll just sample it, right? So, but you get the general idea of the whole process. So I'll wait a few seconds to have for any more questions, because we're going to switch gears. And I'm going to rush through the next topic a bit. Any questions? No questions. All right. So let me go ahead. So this, I assume everything we said so far was clear, right? I'm going to change topics. How many of you remember principal component analysis? Okay. So I won't wait for everybody to raise your hands. In principal component analysis, we try to find a principal subspace such that when all vectors are approximated as lying on the subspace, the approximation error is minimal. So if all of these points represent your data, and you want to find a first principal component, you're trying to find a line of this kind. I'm assuming the data is zero mean. You're trying to find a line of this kind such that when I project all of the data onto this line, which is to say I drop them perpendicularly onto this line, then the total error, which is shown by the total squared length of all of these green lines over here, that is minimized. And so the overall process is going to be something like this. Oh, shoot. This was supposed to be an animation, but you'd start off with, I'm sorry. So I just changed to PDF. So the animation is kind of lost over here, but maybe we can see this in a later slide, right? So what you would do is maybe think of it this way. If you can search through all possible lines, and so this line, in this line, clearly the total error is much greater. For this line, the total error is much smaller. So you search through all possible lines till you find the specific line for which the total error is minimized, and that's going to be your principal subspace. And you can do this in closed form. So for example, any line, or here in one dimension or in multiple dimensions, any subspace can be represented by a vector or a collection of vectors of this kind. And let's say this vector W is actually unit length. Then the projection of any vector on this line is simply going to be, assuming W is unit length, is simply going to be the inner product between the vector X and W. So the difference between the squared length of X and the squared length of this projection is going to be the squared projection error, which is the total squared length of this dotted line. And you want to find the vector W that minimizes this total squared length. And if you work through the arithmetic, you're going to get the standard eigenvalue equation that we're all familiar with when we try to perform principal component analysis. But then there's also an iterative solution. For example, here's what I can do. There are two different things that we are doing when we're trying to perform PCA. In the first Okay. In the first step, the first thing that we're trying to find is the direction of the principal component. The second thing that we're trying to find is where on this principal, the direction of the principal subspace. And the second thing that we're trying to find is where on the subspace does each data project to. So there are two things over here. And so basically, we're trying to find W, and we're trying to find the Z such that Z times W is the closest approximation to X. So we can do this in a two-step process. I can start off by assuming that I know some W, and using that W, I can find the Z for every data vector. Then I can assume that I know the Z for every data vector and use the Z's and the X's for every data vector to find the W. And if I keep iterating through this process, it's guaranteed to find the principal subspace. So let's see if I can. This was supposed to be a PPT. Unfortunately, this is, I'll see if I can actually. I can't do this with a PPT because I'm doing this with a PDF. But so here's what you would do. You're going to have, you would have some data of this kind. And so I can just say initially assume that I have some initial guess for the principal subspace. Then I can project these data points onto this principal subspace, right? And so these are going to be the closest points. But then now I can say that regardless of what the line is, this data point is going to be closer to the center than this data point. And so I can let this line rotate, allowing these points to sort of slide along the line until I get some other data points, some other line where the total error is minimized. And so this really won't work without animation. So tell you what, guys, because I need animation for this particular portion of the lecture, I'll stop here. I'll pick this up in the next class where I'll figure out how to do the animation just right. And I'll sort of go back and let's address the issue of what happens with why some of you didn't quite get what I was talking about when I talked about this. So let's go back and let me ask Vinay. So what was missing over here?
Missing in the sense, I understand. Sir.
Pardon me?
Missing in the sense, like, could you please repeat that and understand what will be missing?
So over here, did you get an idea of what we were missing? To the left. You had all of these vectors, but some components were missing, right?
Yeah. So we were taking like a weight. So every vector would have like, I mean, when we're filling it out, every vector would have its own a posterior probability for every value that we fill in. And that would be
for every missing component, there would be some a posteriori probability, right?
Yeah.
And so and you're going to fill it in according to that a posteriori probability.
Yeah.
Right. And over here, did you understand what I meant by missing? You don't know which Gaussian any vector came from.
Yeah.
So I'm going to be filling in the colors according to the a posteriori probability. Does that make sense?
Yes.
Okay. So Idris, in the picture to the left, this is a pretty much this is an exact example. So how do you think in the past Netflix would give you recommendations for movies? So what they would do was that every person who watched movies would actually give them ratings for the movies that they watched. But then there are maybe 1 million movies and each person has watched maybe a couple of hundred, right? So they have not rated the majority of the movies. So this ratings vector that you got for every person is going to be mostly empty. Based on this collection of empty incomplete vectors, they would compute this overall Gaussian distribution. And then when a new person came in and they had watched some movies, based on the movies that they have watched, they can now use this Gaussian that they have estimated to compute some expected value for these missing components, the movies that they hadn't watched, and then they can use those numbers to recommend movies to you. So this is something that you actually have been encountering if you've been using Amazon or anything that gives you a recommendation. Does that make sense to you, Idris? Right? So this happens everywhere. You use it all the time. Or if you're trying to estimate Gaussian mixtures, same thing. Estimating mixture distributions is a very, very common problem. And we use this solution all the time. And if we are going to be using variational autoencoders or diffusion models, guess what? This is what you're going to be using. Any other questions, guys?
I had a
Does the
question about-
variational
Oh, sorry.
Go ahead.
sorry, does the variational autoencoder replace the Gaussian? Is that the difference?
We will see this, right? I didn't actually get to that. We would have been faster had I been in class, but actually, I think that's a bad idea. I think this is the correct place for me to stop. So we will see how the variational autoencoder works out, but the variational autoencoder is going to be using this basic principle that we just saw when we want to estimate the model. How that whole thing works out has got to be seen, and for that we will do it in the next class. The mechanism itself that we use, that was what we spoke about in today's lecture. Any other questions?
Yeah, I had a question about like maximizing the log likelihood. I can understand the formula behind it, but if we have missing data, then how are we like, what are we like, are we maximizing just our model based on the observed data?
Yeah, because the only thing that you have, what is the only thing you actually have?
What you've observed.
Exactly.
Okay.
So the only thing that you can maximize is, wait, I'm missing the slides, but what you can maximize in every case is just this guy, right? Working with PDFs is very annoying, but the only thing you're allowed to maximize is the log of the probability or the probability of the data that you have actually observed, which is this guy, right? This term to the right, because
Right.
that's the only grounding you've got,
Okay.
right?
And so based on that is what we're
Yeah.
using to fill in the missing data.
Yes. Because the distribution is defined over the complete data. And really, there's no guarantee that you're always going to be missing the same thing in different observations, right? The complete data are complete, right? I mean, they go across all components. For example, in my movie rating problem, the movies you didn't watch are not going to be the same ones that I didn't watch. And so the distribution is over the complete data. Any other questions? I guess not. So